happy, Josh, for you to be here and to close off the talks for us. Looking forward to your insights.
Sure. Yeah, I hope this talk's going to be interesting. It's definitely maybe a little bit different of a talk, I think, from a different perspective, which I hope will be valuable to lots of people. Yeah, as far as I want to say, this was at least the first part of the talk. I don't want to implicate my collaborators in the speculations. Is done with the work of like some really awesome people, Eric Rashad, Isaac Lau, Wes Gurney, Max Tegmark. Yeah, so I guess I'm thinking I'll just kind of first give an intro of like what mechanistic interpretability is all about. I mean, we've seen a little bit from like Adam's talk and Paul's a little bit, but yeah, feel free to interrupt me a couple times or ask questions. You know, I'm sure that there are like things that I will take as like that are obvious that won't be, so don't feel bad about asking like any sort of question. All right. So first, like, what is this whole mechanistic interpretability, mech-interp thing? There's been first, like, an interesting question is how does this differ from like other types of like science of language models? And I think the thing that really differentiates it, that is kind of why it's come into its own field in the last 3 or 4 years, is a real focus on understanding things from the bottom up, from like taking neural networks and trying to basically reverse engineer them, completely figure out like exactly what they've learned internally, like open up the black box, quote unquote. You can do a lot from looking at like, oh, like giving this, it's kind of like, you know, neuroscience, right? You can do a lot from like just doing like psychology, just seeing what happens when you give models prompts, but you can, the idea is hopefully we can learn something else from looking inside. So one avenue, which is kind of similar to Adam Paul's direction, is you can look at, cursor is, sorry.
I heard you talking about it.
You heard me talk about it, exactly, wanted attention. You can look at toy models and kind of like try to look at the representations they learn, and then maybe try to really understand toy models super well. And so here I could just easily have had, you know, their recent work here, but I put this stuff on modular edition. So this is where, like, basically, you know, you have 2 inputs that are like numbers between 1 and like n, where n is like some prime, and then the output should be the sum of those 2 numbers, and the goal is to figure out how the model like learns to do this task. And there's like a bunch of different ways that the models learn to do this task, but there's kind of like, we've kind of discovered maybe there's a couple classes of ways, like these are very small models. One way is they kind of map numbers to like points along a circle, and then you basically add the angles, and then map them back from that angle. Another, that's kind of like doing it in the Fourier space. Another way you can do it is you can just kind of like average, like again mapped to points on a circle, but instead of adding the angles together, you can just kind of like average the 2 lines. And so like, you know, we have like 1 and 4 mapped to the same place 2 and 3 go to, because it's averaging them, so you're like, oh, that's 5, you know, like any, that's like the pizza algorithm, and the other one of those is the clock algorithm. So anyways, my work in this talk is inspired a little by this modular addition stuff, but specifically looking at like LLMs. So this is kind of like, you can look at toy models super closely, but you can also look at language models and kind of like attack the problem from that end. And so like here's some work, some really cool work, finding this like indirect object identification circuit in GPT-2. So indirect object identification is like this linguistic task where I say John and Mary went to the store, and John gave an apple to blank. And the goal is the model is supposed to predict Mary, because that's like the correct thing to predict there. And it does this successfully. And you can kind of figure out exactly how it's doing this. It's like looking back and saying, oh, John occurred twice, but Mary occurred once, so therefore I should put Mary here. And you can actually like figure out the circuit for this, which is just a fancy way of saying like the pieces in the model that compute this task. So anyways, that's kind of the 2 different flavors of mech-interp, and they're kind of working towards each other, and hopefully we can, just as rigorously as we understand toy models, we can understand big models. Right. So our focus is going to be on like the variables that models use for computation. Here is like a screenshot from the same work that Paul talked about, the platonic representation hypothesis, showing a bunch of different representations of color in a vision model, a language model, and also human perception. And the neat thing is they're like all kind of similar if you squint a little bit. Like, you know, like the yellowish orange colors in the top right and the bluish green colors in the down left, and like, so basically, like, this is kind of saying that maybe, and there's a bunch of reasons for this maybe, but all of these kind of representations are converging, and so maybe we can just study one or two models, and that's kind of tells us something pretty interesting. So we're just going to study a couple models in this talk. Right, okay, so also a quick reminder on how LLMs work. I think Adam talked a little bit about this, but I'll give kind of the angle that'll be interesting in this talk. So basically we have some tokens, they get embedded, and then there's like a bunch of layers that kind of just continuously operate on this these lists of embeddings. One thing is attention, which basically mixes these representations together, and another thing is NLP, which is kind of this computation on each token. So yeah, and then what we're going to be looking at is not actually even worrying too much about attention and NLPs and anything, just looking at I don't know I'm going to use anthropomorphic language in my talk because it's my talk. What is the LLM thinking at each point? So after one layer of attention NLPs or after two layers of attention NLPs, what is the model thinking? What are its residual stream states, like these states, and what do they look like? Right. So how are representations stored in the residual stream? It would be really nice, it'd be super simple if you have these 4,000 dimensional vectors. If one dimension, each stored a single constant. That would be great. Unfortunately, that doesn't really happen usually. And it's kind of impossible for it to happen because an LLM knows way more than 4,000 or 10,000 concepts. It's like this bottleneck. And so here's Chris Olaf, who's one of the founders of MechInter. This is having a vision model, looking at a single neuron and kind of figuring out what are the classes of things that most activate this neuron. This is some cool visualization technique where you kind of find max activating examples.
These are receptive fields.
Receptive,
these are the receptive fields of these neurons.
Yeah. Yes, these are the things. Yeah, exactly. These are the things.
Are they average? Are they well approximated by the average input that gives rise to a response, or is it really not? Is it super nonlinear neuron where you found this is the thing that activates it the most? The specific input.
Yes, these are specific. They find this with gradient descent, I think. They basically run gradient descent a couple times, and they find there's different. I don't actually remember exactly how they, but all these things very highly activate the neuron. But maybe not if you took linear interpolation between them. I don't think everything in between would highly activate the neuron.
Yeah, it wouldn't the average wouldn't look cat-like. Or
The
something.
average, the average.
That's the specific thing I'm wondering. Yeah, if you were just to show a bunch of images to the input, and then based on and weight them by the activity of this. Of this unit, do you get a similar picture?
I think it would look like noise.
You just get gray.
You just get gray.
Or noisy gray.
Yeah. So this is cat legs and cars, and the idea is not that I think the idea is not that there's some feature that's it's good. It's the model's representing cars and cats in the same way, right? There's some downstream thing that needs to represent cars and cats the same way for it. I think that's not the case. What is the case is, what I'm going to get into is that there's some other hypothesis that this neuron just participates in the representation of multiple concepts. I don't think this is a new concept for all the neuroscience people. Distributed representations are a thing in neuroscience too. Okay, so what's the solution here? There's this hypothesis that everything is a linear representation in language models, just a line. And the way we can kind of cram more than the dimension of the residual stream is we have them be kind of all almost orthogonal, and only a sparse number of them are active at any given time. So here's an example. Say you have this sentence: the orange cat jumped. We say this is superposition, but it has nothing to do with quantum. We say the orange cat jumped, and then we can look at the embedding. We can break this out, and you can kind of see maybe there's all these different directions for dogs and cows and Japan and Boston and all these things. But only the concepts that are active in the sentence are actually fired. You might also say, well, how do we know it's the orange cat jumping and not a cat jumping over something orange? So there might be there's still kind of a lot of unsolved problems here about binding and how this all works. I'm gonna get to that later, but for now this is kind of the picture. And the cool thing is that the Jordan-Lindström lemma says that you can have an exponential number of almost orthogonal vectors, and that you can kind of decode these as long as it's sparse with not that much interference because they're all almost orthogonal. Yeah.
Sure, exponential in the
In
dimension.
exponential dimension of space, exactly. Yep. Yeah, I think the construction's super easy. Just like you choose like random vectors, and then there's some like bounded probability that like they'll all be a certain distance apart from each other. Yeah.
And then with sparsity, you can basically recover it with some. Like,
Yeah, the sparsity, exactly. Once you have sparsity, like imagine like we want to have a projection for feline, we can just kind of like choose a vector that's like pretty parallel to feline, but like as almost orthogonal as possible to all the other vectors, and then like most of the time in a high dimensional space, that vector will have like not that much interference. Yeah.
But part of the reason to encode it in a linear space is to have non-orthogonality between concepts.
Well, maybe this is part of what we argue, but technically you don't need non-orthogonality between concepts. Like the original linear representation hypothesis, like doesn't talk anything about the structure of concepts in relation to each other. I think that's super important, and people are kind of starting to get. That's a lot of what this talk is about. That the geometry of concepts are important, but that's like kind of a recent thing. Yeah, yeah, interesting.
we think so. You think so?
I think so, but yeah, like this is not like people. Yeah, I'm gonna get into this. So this is maybe like you said, excellent point. This is like kind of an incomplete picture if all we care about is almost orthogonality. So there's limitations about these. Here we go. You predict this perfectly. You have very good. You're very good future predictor. What is the relationship between feature vectors? Can we say anything more than almost orthogonal? Are these 1D vectors really like the correct model of an atomic feature? What types of features might be inherently multidimensional? Like what would they look like? How can we find them? Okay, these are the questions that hopefully I'm going to answer in the next few slides. This is the multi-representation hypothesis. So before we get activation of sparse linear combinations of meaningful feature vectors, now we're going to say that actually activations are sparse linear combinations of meaningful feature manifolds, aka like multi-D features. And each of these manifolds, each of these multi-D features are not just like these like almost orthogonal things. So here are some examples of things we actually find in language models. The coolest ones are the two left ones, I think. I'm going to get into how we find these and like what these mean. But basically, you look at a language model's brain. You take a very large number of prompts that all have to do with like days of the week. You basically project out the interference using this thing called sparse autoencoder. And what you find is that like there are these like features where the structure between the features matters a lot, and they have like this interesting structure, circular structure, in fact.
You're calling these manifolds?
Yeah.
Like, I mean, there's a differentiable surface here?
The points lie on a manifold.
Yeah, it's not like that has nothing to do with the derivative. I guess I call it manifold because like there's kind of like some continuous curve that means something around the outside. That means like that's like this kind of like a time.
Okay, but you're not discovering like a surface, a differentiable. I mean, when I think of a manifold, I'm thinking of something that's laying like a differentiable surface laying in a.
I think you can say roughly it seems like these points lie on a conical surface. So,
yeah, sure.
But
you're
it's
not
not
like learning a description of that. This is purely like you're looking at it and saying this looks like it might lay on a manifold, but there's no description of what that would be.
Well, we like to learn a circle. Like we will learn a circle that best fits this.
But it would be like using like library function matching to do that, right?
Yeah, it uses like linear regression, kind of like what Paul, like kind of what Paul was
doing. What I'm saying, I guess my point is like the mathematical way that you're doing this, you don't arrive at a description of that circle. You could like look at it and interpret that it might be a circle.
Yeah, we're not predicting the circle's going to exist.
Use some Fourier thing to try and get a description of a circle, but it doesn't come out of the.
There's no math. There's no math.
Okay.
I wonder if
no math at all.
I'm trying to think
There is
ahead.
some math.
So if you wanted to turn time, instead of months of the year, days of the week, you wanted a continuous manifold out of it. I wonder if you gave it prompts with times and days or dates of the year, whether it's 365 or whatever, if you can get it, I don't know if that
like more, you
that's
think like more,
but I mean,
more continuous?
You could get it more continuous with a data set or with a set of questions.
Okay, we have this. So this is like on days of the week. You can have like early morning Friday, evening Friday, late. So it's like a little more continuous now.
Right, and then you can imagine taking this further. I don't know.
Yeah, it's kind of hard to get it to go further. Like this is
Yeah.
like, you know, this is like somewhat cherry picked. Like 2 p.m. on Friday doesn't work the same way.
There is a discrete nature to this kind of data set.
Yeah.
But I wonder if it gets enough. You know, if you start putting in 2:47 p.m.
Yeah.
Monday, you know, or whatever.
It doesn't quite work that nicely.
You know what I mean?
I think it's because only if it's like useful for the model. Like 2:47 p.m. on Friday is probably not something. Probably just encodes Friday and then also encodes 2:47 somewhere else.
Yeah, maybe.
There might not be one representation where it's encoding that closely.
Anyway.
Yeah.
So, sorry, I still wanted to understand the plots, the manifolds here
Yeah.
a little bit better. So
Yeah.
it looks like a sort of semi-random scattering of points.
Right. Okay. So let me maybe I can get into exactly how these plots are generated.
Is this like learned instances of the word from your data sort of being trained into?
This is we're not training any models, but this is
Okay.
like across the whole corpus of text,
Uh-huh.
like a very very large corpus. Like, what are all of the all of like this is like plots of like any context that like Tuesday occurs in, like kind of
church
share.
is going to be Sunday or something.
Exactly. I don't know if church actually shows up on here, but it's something like
That's
that.
the
Like
kind of thing.
it could be there, or like there's lots of other. Most of these are just like different contexts that have the word Sunday in them. But some of them could be things like I don't know, like Taco Tuesday, maybe tacos are wrong on Tuesday or something.
Right.
Then is this the activation at the position where that word occurs? Or
It usually is, but there's no like regularize. We're not like regularizing. We're not only looking at things that end in that word. It's anything that fires in this space.
you take the whole context and then you look at the activation at the final position.
No. Let me
Okay,
how
you
it's
should
generated.
explain
How it's generated. So okay, first I'm going to define what we mean by multi-D features. I think this is like most of the math we talk. Maybe it's interesting, and maybe you can tell me places that this is stupid. But we say that like, okay, how do we tell a difference between like something that's like actually intrinsically multidimensional versus something that's just like, I don't know, a combination of lower dimensional features? We say there's kind of like 2 things that make something reducible. First, if like it's just 2 things that are like independent. If you can decompose this distribution, this potential feature distribution into 2 things that are like independent and lower dimensional, then probably it's not a real feature. So for example, like if you have some like a Gaussian, for example, like there's always some rotation that gives it like a diagonal covariance matrix. So a Gaussian is always like reducible in this manner. Or like if you have 2 things that aren't related at all, like I don't know, it doesn't quite work because the Earth is like a sphere, but the Earth is like not uniform. But you can talk about latitude and longitudes. Even though these things do have some mutual information, like there's not that much. So maybe we'd say these are also independent. And then another thing you could say is 2 things that never occur together. We also, at least in this definition, don't really want to say these are a multidimensional feature. So things that are like very, very strongly anti-correlated. So here it's like a simplex where you have like something that's either a bird or a mammal or a fish or a reptile. This is something where, you know, these things don't occur at the same time, but and so they have non-zero mutual information, but we don't want to say that that they're part of the same. That we still want to say this is reducible kind of into like these like kind of features. But like a circle, there's no projection. There's no
Why?
Why do we want to say this is?
I mean, I kind of get it, but I guess
Yeah.
maybe you just say more. Like,
Sure. So like, is the question like why?
I guess I would think that is an interesting structure. That you
I guess because I would think the intuition I think is that like so many things don't occur together.
so
Like
it's too common.
it's too common. Like submarines and weather, or like submarines and cats. Very
right,
like
but
together.
I guess my intuition would be like with this example.
This example comes from a paper where they're talking about hierarchical structures.
Okay,
So-
so like this example seems like it would be useful to be
Right,
full.
but like you need some other framework for like why this is interesting, why this is like a
you
real
have to have the
multidimensional feature.
context of it being all of those are animals.
Yeah, like
Yeah.
this work also has some problems maybe, like that people discovered that like lots of things are on simplices, like not just things that you actually want to be on a simplex.
Oh, interesting.
Just because of like problems with data analysis.
But then the days of the week is one dimension, for example, or
Sorry, say?
the days of the week.
So days of the week is here. It's still like a little bit reducible in this sense. So we actually like we can soften these definitions to say like how much of each of these properties the distribution has. And actually, when you do this, you find that like the days of the week stuff are are the most irreducible by these metrics. Like these are not perfect metrics because in practice, so a circle, a perfect circle would be perfectly irreducible by these metrics. But like in practice, we have like more discrete things, and it's hard to estimate these quantities.
But what I'm confused about
Yeah.
is that the different days of the week never appear together. Is that what you mean by they don't appear together? It's like
the days, that's what I'm saying. This is not a perfect. Like the way we operationalize this definition of like disjoint lower D features is like, is there like some line along which like a very large measure of the distribution lies? Because if that's the case, then like probably that like line or that low dimensional feature is like something separate.
I guess like intuitively, like some of these interesting geometric relationships are because of how the concepts relate to each other, like that Thursdays to Friday, as
Sure.
Mondays to Tuesday, and then something like this orthogonality, it's like, well, we don't usually, like, there's not so much about how they relate to each other. There's still something maybe in some very abstract version, but
Yeah.
right, does that seem fair to you?
That seems fair, yeah. I mean, I guess these are all certainly not perfect definitions, but it's kind of weird. These are like these are kind of like descriptive definitions almost. Like we found these interesting structures, and we're like, how do we differentiate these from like other structures that you might like? How do we say this is interesting, other things are not interesting? Yeah. Okay, so how do we find these things? Well, we take inspiration from the way people find one-dimensional features, which uses sparse autoencoders. So the idea is that you have something like this, many different examples, and you kind of hypothesize that all of them are these like sparse sums of like true underlying features. We train an autoencoder to basically predict this same space, but internally you can only have like a sparse set of latents active. So like you take your initial projection, you up project it very wide, you add a sparsity penalty, and then you down project it back down to try to reconstruct it. So the idea is like, this is feline, and this is orange, and like there's one more for action, and in this case, you would just get those, and then that would reconstruct the outputs. And so like the idea is like we're trying, like this is something called dictionary learning, which is also a field that's been studied before like MechInterp has like co-opted it, but so the idea is like you basically want to learn like the dictionary of vectors and also their weights, and you can do this with the sparsity penalty. But okay, how does this help us with like finding multidimensional features? The key idea is that if you have something like a circle or some super continuous kind of feature like this, there will be like many high similarity dictionary vectors that are going to be learned to reconstruct the circle because of the sparsity penalty. And so if we cluster the features, well, basically we can look at each cluster, like look at the reconstructions of the SE restricted to each cluster, and basically run our statistical tests on them. And so like if you look at this, like the clusters that it just so happens that if you kind of investigate these like highest scoring clusters, they look really interesting. And so like this is kind of like we have this statistical test, and when we apply it to the cluster sparse autoencoder vectors, it like kind of automatically finds these features. So this is actually entirely unsupervised. We can just totally just like take the brain of a large language model, like decompose it into concepts, then cluster those concepts, and we end up with interesting multidimensional structure.
Wait, can you explain that scatter plot a little
Yes.
bit?
Okay, so there are these definitions. There's I would say like separability, which is like how separable are you into independent distributions, low dimensional distributions, and there's like mixtureness, which is like the second one, which is like how much are you composed of like disjoint low dimensional distributions. And you can have a test for each of these. So for separability, you can figure out like what the best rotation of the space is that minimizes mutual information between like the two axes, let's say. And for separability, for mixtureness, you can find like a projection of the space that like has the most points lying along it, like a low dimensional projection that has the most points lying along it. And so like those are what the two axes show, like applying this test to all the clusters. And like these interesting clusters are like do the best on the test. Okay. Okay, so I'm saying we find some on Mistral as well, and there's like some other cool stuff, like this is the weekend and it lies in between Saturday and Sunday. It's just a bigger model. And yeah, like winter, spring, summer, and fall, like fall in between the months of the year. So where you expect. So that's cool. So kind of the second part of the results, how are we doing on time, by the way?
Well, you're at 25 minutes,
Okay.
so I think you're
Yeah.
good. Another.
Cool. Yeah. I'll briefly talk about some of the use case, like some of the investigation of how do models use these circles, and then I'll move on to speculations. So yeah, I guess one interesting thing you might say is like, okay, we find this structure, and maybe we have some weird definitions for like why we think the structure is real. But like, do models actually use this structure, or is it just kind of like correlational and like not actually used? I don't know. I guess this is a distinction that I think is pretty interesting. But I don't know. I'm curious. Maybe people have thoughts about this from like the comp mech perspective. Like there's like, because it's kind of like, well, maybe one reason you would have this structure is to try to better predict the future. But another reason you might have this structure, and so that's kind of what I'm interested in. Like there's this structure and there's this compression. Like you only have so much space. And it's like takes less space to have a circle that you rotate instead of just having a lookup table. Like a lookup table kind of takes, you can kind of think of it as like having to memorize like, I don't know, like a bunch of bits, like for every possible combination of like what's 3 days from Monday or something. That's what this task is. Like 2 days from Monday is blank. Whereas if you just have a circle and you learn that, you know, asking a question about 2 days from now is equivalent to rotating the circle, it's kind of like a more general algorithm. So this is similar in some ways to like what the modular arithmetic work looks at, like grokking, like when do models generalize? Yeah.
To me, this seems very tied to your work. Like, you know, computational mechanics, as it's been done for a while, is very much, you know, semantics free. You know, the closeness of tokens or symbols didn't really play a role. But once you start to have like a distance between them, then that adds additional meaning.
Definitely some of the intuitions are the same. I mean, I think the difficulty here is you don't necessarily know, like, because you're projecting everything up into random Fourier features or something anyway, like to get this orthogonality. So you're kind of starting there, which you inherit a bunch of geometry from that, and then the model maybe learns some geometry that might.
There's not any
there
random.
may be relationships between these things.
There aren't any random projections.
Did you say you choose like to try and get in everything orthogonal to everything else?
So that's the model learns all that.
Yeah.
So this is all like learned. Like we discover the structure. Like
but there is a utility function that optimizes over that, right?
no. So the model's only trained to predict the next token.
Okay.
But internally, we like the hypothesis is that it develops all these almost orthogonal concepts.
Okay, so you've shown that just empirically.
Yeah.
Okay.
There's some theoretical work showing that under some cases there might be reasons to live linear
I
representations.
think I would interpret things differently. I think what's been shown is that if you assume that structure, you can to some degree reconstruct the activations in the transparency.
That's true. There could be other hypotheses that also would give rise to the
It's
result
like
we've seen.
largely, I would say, the evidence so far is consistent-ish
Ish.
with,
Yeah, Jake would say
with that
something else.
hypothesis. Yes.
Yeah, I mean, I think that's why it seems so difficult. It's like
Yeah.
phenomenological in a very, but it's like, there's a lot of unknowns, and there's probably a lot of unknowns.
Yeah. I mean, it's experimental science. It's like
Yeah.
a real experimental science.
Yeah, like it really is just like we're coming up with like hypotheses and then testing them, and maybe they'll be falsified.
I wonder how much of this is relying on this linear algebra or orthogonality. It all kind of smacks of just looking for kind of independence and minimizing projections on subspaces. One thing is, are there other kinds of statistics we could use, like these other kinds of information atoms, other kinds of conditional distributions or conditional entropies and conditional neutral information, that give just a different geometry to the space?
Yeah, I did have that thought. I mean, like if you're looking at, if you're trying to understand how these things relate to each other, and like, I mean, so there's a good Ryan Jacobs article where he sort of talks about correlation versus like different information atoms, and he actually uses the circle as an example of like the advantage of using nonlinear things like mutual information, et cetera, and other information atoms to compare distributions, because 2-point correlation stuff just flattens a lot of the interesting structures that I would assume exist within.
So you're saying like, look at, like take these like these structures, right? You're saying, because this is basically like a projection. I mean, we can just think of it as like a projection of like all of like the weekday related concepts, like this like subspace, right? And we say like, okay, this is like some concept that the model has, and it's like mostly contained in this 2D subspace. And you're saying like, look at the mutual information between.
No, what I'm talking about is like that earlier than this, when you were, or so I'm not sure quite what the ordering is here, but like when you have that plot up of like the clusters, and you're trying to describe how irreducible they are, and it's like there's different ways in which you can do that. I guess, I mean, my immediate thought when I'm thinking about like, okay, I'm looking for like irreducible things in some distribution, I want to describe a distribution, is like I'm going to look at the information atoms over that distribution, and like something that is organized like a circle is going to be distinguishable from information theory, but not from like Pearson's correlation.
I think that another maybe way to frame what you're saying is more.
Are you saying like different? You want like different tests? Like
well, I
different,
don't know, because
Yeah,
I didn't say this because I don't know what those tests are.
Yeah,
So
I don't
that's
think
what
those tests are.
I think
Yeah.
another way to maybe frame what I
Yeah.
think you're saying and what I think is your language is something like you're doing this funny thing where you're training the SAE, which assumes a kind of linear sparse structure. It assumes a particular structure, and then you're going backwards and trying to find circles.
Yes.
And I think the suggestion is, well, maybe there's a different metric. There's a different way to look at the structure that's more direct, that more looks for kind of manifold.
That would be good. I tried it.
But
So
also qualitatively different kinds of relationship. Like, take a look for, if I have these things, what other variables make them conditionally dependent or make them conditionally independent? There's a whole hierarchy, structural, that kind of semantically interpreted relationships we talk about, not just kind of standard ones from statistics.
Well, belief geometry.
Yeah, I mean, the reason I didn't like say any of this when we were going over it is because I don't know exactly what those are. I mean, you gave an intuition for them.
yeah,
But-
these are certainly just like intuitive. Like maybe there's better ways. There's
Well,
certainly
I'm not-
better ways to distinguish circles from like other types of things.
Yeah, but even like, I guess when you say you're searching for circles, I'm like, okay, that's interesting because that is like more than just looking for correlation or something. So it's interesting in and of itself. Like it's already kind of an interesting thing. But then that's only one type of geometry. So
I think. Well,
I think my guess is that this is the first stressor, and I think ultimately my thought would be that people would want to say like, okay, now we just don't care about circles, we care about kind of arbitrary geometries
So
that might exist.
this can find things besides circles. In theory.
Okay, that's just your example.
Yeah, so like I mean, if people are interested, like there's some other stuff it found. Like so, this is let's see here this is like days of the week cluster. Like as we like these are like different projections in the different PCA planes, and these are like the highest ones from up here. That don't always are open R. And then this is like some other interesting structure that's like a lot of the letter A. Like so, I'm mostly over these are different contexts that produce these points on this plot. And so like maybe this is like some interesting other type of structure that we find. So I don't know.
To what extent can you use dynamics to find the structure?
That was the other thing that I was
Just
interested
get a
in.
bunch of things and then see how it's moving.
Yeah.
How the activations are moving.
See what's moving? How would that
feed it different inputs?
Yeah.
See what activations light up in the space over time.
Yeah. So that's like it's kind of what we have here because like you can mouse over each of these points and see like what the text was that activated it, right? I mean, it's quite short, but it's a lot of like, as Aaron was talking about earlier, it's a lot of just like staring at this stuff and trying to figure out like what, because we don't really like, it's hard to like, these are like in the middle of a network, so it's hard to like choose something that we know is going to activate this single point, right? Like it's kind of like if you, how do I know? Like I can observe over a very large input distribution what occurs in each point of this plot. But I don't. It's hard for me to make a very controlled, like, oh, I want to move along this part of the plot.
Yeah, I mean, because that kind of was the second part of what you were saying, comparing this to like, Compact work, where the points that you're looking at have the dynamics embedded within them.
Yeah.
And then you can, like, the geometry of how close they are describes their distributions over futures, but there's like another aspect of that, which is that how trajectories move in quantum space.
Yeah. So
Right.
this is
And
something.
that's-
I've been trying to annoy you about, like, to no avail for the last few days, which is like a lot of the analysis is done kind of in a layer-wise fashion, but really kind of if you take the mixed state seriously, like their purpose is to update in context.
Exactly.
Like that's their functional role. That's the reason why they're represented inside.
Yeah.
And so if you can use a method that finds representations that takes that functional role into account somehow, that could be
Yes.
nice.
I
But
agree
exactly
that
how
we-
to do that.
Yeah, no, I
Yeah,
understand this is hard. I
Yeah.
just think like if you want to, like if you're looking for connections, that would be the big
Yeah.
thing,
Yeah.
right?
Yeah.
Where it's like some kind, I'm not even sure what that would mean in this context, but like
Yeah, I mean,
some
there's,
sense of a dynamic.
there definitely is some sense of dynamic because like Adam was saying, like we have multiple tokens, right?
Yeah.
So like you're at token 5, you want to predict token 6. Now you're token 6, you want to predict token 7.
Right.
But a token 6, the thing is like this representation might be totally gone. It might only be present at this one token, and then future layers can always look back, and future tokens can always look back and use it.
Yeah,
but-
that's another annoying thing, right? These things are not constrained with a single internal state
Yeah.
that markup shields the past from the future.
Yes.
They always have access to everything before it.
Yes.
What do you mean? It's not recurrent.
No, it's actually recurrent would be easier.
Yeah, that's what I'm saying. It's not recurrent.
Yeah.
So there's
So
no
like you can,
bottleneck.
because of
inside.
attention, if you're in any future state, layer 10, you can always look at all of the earlier tokens that are at
Right.
layer 10 and like combine them and then do something with them.
It's carrying around.
It's carrying around exactly. So it doesn't actually ever update this state directly. It just kind of keeps it, and future states can take it and manipulate it if they want. Future tokens. So it's kind of hard to track what happens. Like it'd be really cool if we could track what happens as representation.
Yeah, that's kind
Right?
of yeah.
But maybe that's, I don't know, maybe there's something there we can talk about. Yeah. Okay, let me briefly talk about like some of the experiments in the paper, and then I'll talk about speculations. So, okay, yeah, this is a modular arithmetic problem. We're very curious to see whether models actually use these circles for the modular arithmetic. GPT-2 can't do modular arithmetic, so we look at Mistral and Llama. And it turns out, I don't know what I'm talking about. It turns out that if you actually intervene on the circle, so we take the circle and we look at whatever point was there and we just remove it. So you don't really look at it. And then you just change what the representation along the circle. Then the model basically acts as if that was as if you have changed the internal representation of what the current data week is. So if you ask the model, today is blank, what will be in 2 days, and on the blank token, you change the representation on the circle to be all these points. It doesn't just work, we learn this circle by looking at the edge of the circle, but even in the middle of the circle, all around, it basically respects this circular geometry. I don't know, did I explain that well? Does that make sense?
I did not follow.
Okay.
Sorry.
Yeah. So
Just use a specific set of days of the week names.
all right. So say I say it's currently Monday. What day will it be in 3 days? Right.
Right.
You should say Thursday. Right. Language models can do that. And now I'm going to go into the language model's brain. This is the 3 days one, so it's up here. And we say, well, it's currently Monday. What day will be in 3 days? Well, Monday, let's say, is I don't know, right? Monday's this point right here, right? That's how it's represented. And then I'm going to erase that and change the point, using this targeted intervention, just in this subspace, to up here. And the model then predicts Saturday. And if I change it to right here, the model predicts Friday. And if I change it to right here, the model predicts, Thursday or whatever.
Okay, so you can move around.
You can move
So
around
it
the
does-
space.
It does the correct phase rotation
It does the
if
correct
you do an
phase rotation, yeah.
intervention.
So
Exactly.
so it is using the relationship.
It is using this
between
circle. Yeah, exactly. So basically this is showing that it's a causal representation. The circle is causal. Yeah, and the other thing I talk about this is that you can show this are a little more continuous, which is cool. And it's not that interesting. Okay, so recent follow-ups. So Chris Ola kind of took offense that we named this not all language models linear features are linear, and kind of breaks it down into two types of features, two types of parts of the linear representation hypothesis. One is that features are one-dimensional, which we kind of rebut, and the other one is that the feature magnitude correlates with intensity. So which we don't rebut. So like being further out on the circle maybe means that like you're more Monday or like more Tuesday or more Wednesday. So then recently in like a toy RNN setting, because this group Casores et al., they show evidence against part 2 by finding these really, really neat onion-like features over here, where basically if they're trying to memorize this sequence of letters like A, B, C, D, E, you know, like all these things, the way that RNN learns how to do it is they put like the A representation on the first token representation on the inside, and then each successive token representation like going out like in an onion. And then when it's trying to unwrap, when it's trying to regurgitate the memorized sentence, it like unwraps the onion. And this is like very nonlinear. Like if you it's representation. Like if you take any individual direction, then scaling that feature does not mean just intensity. It actually like changes the domain that you're in. Like so now it's not, now you're not talking about the first token, now you're talking about the second token. So this is a big problem. If these actually exist in language models, it's kind of like a death knell for SAEs, for sparse autoencoders. If we're just with R type multi-D features, maybe you still use sparse autoencoders or modifications of sparse autoencoders that kind of like try to just like are aware of this multi-D structure. But if really like scaling a feature changes what it means, then sparse autoencoders are like kind of doomed.
Do you mean doomed as like giving insight into what's actually happening?
Or I mean doomed as in like they'll never tell us everything that's going on inside these models. Like they can still tell us
a current assumption?
Depends who you talk to.
Okay.
Yeah,
Seems quite
I
strong.
can tell you how we know that it is. It's because all 3 of the big companies that spend, you know, the money that we were talking about before on these models, and they pay loads of researchers with PhDs a lot of money to train exactly these things.
Okay.
Yes.
Yeah.
So the resources are flying here. Like
Right.
probably people are spending like on the order of hundreds of millions of dollars, tens of millions of dollars training these SAEs.
Yeah.
It's the dominant way people use to look inside right now.
Yeah, well, it's like it's super. It's been about. I decided to give a history. This has been like the last year or so. This has been super hot, and it doesn't quite have as many use cases as we would like real world use cases. Like you can use it to like control models. Like you find this cat feature, this Golden Gate Bridge feature. You upweight the feature, and now the model talks about Golden Gate bridges. But like we can kind of already do that. So is it differentially better at that? Like I have some work I recently saying maybe, but it's certainly like not getting us to the point where like it's telling us everything we want to know about language models. There's some hope, like especially Anthropic has been like kind of leading the charge here. And Chris Ola, and he's like hopeful that this is gonna like be the answer. I'm a little more skeptical personally. Yeah, so I guess I can go into some of these like speculation slides. They're just kind of all disconnected thoughts, but you know, also happy to talk more about any confusions people have about this stuff.
Yeah, well, we're just so you know, we're at 42 minutes.
Okay.
So I think if there are clarifying questions, it would make sense to do those.
Yeah.
But I'd also love to hear your speculations. Maybe you want to take 10 minutes for those speculations. So, but maybe clarifying questions make sense, right?
I just wanted to ask you what
Yeah.
this other thing that found the onions.
Yeah.
How is that different from the autoencoder?
How is it?
Was that using?
Oh, so they found onions not using a sparse autoencoder.
What
They
did
found
they use to find?
Did
They-
they
this-
engineer them in?
No, actually. So they trained this task,
Yeah.
and they probably suspected there would be onions because it's kind of a natural way you memorize a sequence if you have an RNN. Like I don't know, maybe natural to them. I wouldn't have predicted personally, but okay. Because you can actually pack in more if you represent each. They have some theory in paper. If you represent each token you memorize in like a different direction or something, then you have less space than if you pack in this onion-like fashion.
Yeah, sure.
So that's why the RNNs learn onion-like fashion. How do they prove that they do an onion-like fashion? I can direct you to the paper.
Sure.
They have quite a cool technique for doing it. But they don't use sparse autoencoders.
I see, but they're also using a toy model.
Toy model,
It's much
toy model.
smaller, so it's easier to look at.
Exactly.
You don't need
They're
to say-
only training on this one memorization task. So that's why they haven't shown this in a real model yet. They have some, in my opinion, annoying words to the effect of the paper of we have good reason to expect that language models will also have these sort of representations, but they haven't shown that. So yeah.
Thanks.
I mean, is it totally unreasonable to believe that you have those, but then also have,
Yeah.
I mean,
Also,
I guess I wonder, like you said,
Yeah.
the depth for
Yeah.
autoencoders, but it feels like, I guess my assumption would have been that autoencoders could get you some amount of the way.
Yeah.
And even if these onion-like features
Yeah.
exist, they'll still be able to get you that far.
I agree. I totally agree. Yeah. So this is people have been talking lately about the weak linear representation hypothesis, where like some large fraction of features are linear, but there's other types of things in there.
That would be
And so maybe sparse autoencoders can give us the part that's linear, and then some other techniques can find the other stuff. But it's harder because like once you go to nonlinear representations, you can kind of have anything. Maybe these guys are like, well, there's only some things that they learn. But it feels like a much harder task now that like anything is possible. Whereas like if everything's linear, it's kind of tractable. Like we have some direction.
Yeah, but I mean.
Yeah, but it is the way it is. You can't wish it to be as something else, right? Yeah. Okay, I'll speculate a little bit now. All right, there's some open question on multitude features. This is not that interesting. Basically, I'm just like, I think we leave some questions open in our paper about like exactly like, is the model really rotating the circles? Is that the best way to think about it? We have not shown as much evidence as in the toy case that this is truly what's happening. All right, this stuff. Okay, talked about this. Big open question, I think. Are there true nonlinear features in language models? I'd love to see that. Okay, are SAEs missing features? Kind of related to the last thing. This is some recent work I've done. There's like, the correlation of the mistakes SAEs make is very high as you make SAEs bigger. So the idea is that the main way people make SAEs better right now is they make them really wide. They say like, oh, maybe the SAE has 1 million concepts. Oh, there's still some stuff we haven't explained yet. Let's add 1 billion concepts. But it kind of turns out that like the tokens that have the biggest error don't really change. So like there might just be some like inherent stuff that SAEs are missing. And then you can also like characterize the stuff that the SAEs miss. And not only does it stay constant, but there's large components of it that we can linearly predict from the input activation. So like it's kind of saying that there's like whole subspaces of the activations that we're kind of like missing. So this seems like a problem, and I'm worried about it because Anthropic is spending, tens of millions of dollars. Everyone's spending all this millions of dollars, and like maybe it's misguided. So that's one speculation. Another thing is like RSA is actually useful for anything. So like there's a bunch of things we know they have problems with. Composition, which I mentioned earlier, like if we want to represent like the cat is on the boat, but we just have a cat in a boat feature. How do we know that it's the cat on the boat instead of the cat under the boat or the cat next to the boat? So kind of a story for that would be good. Numerical features, they don't really represent that well. Hierarchy, that there's what we find is that as we make SAEs bigger, you have one concept like mammal, and then it splits into like dog, cat, and birds are mammals, yeah. And then they're not? Oh, okay. Dog, cat, and I don't know, bats are mammals. Human, yeah. And then you scale more, and then the dog concept splits into like, golden retriever and poodle and all these things. And so like, I kind of view this as like there's some sort of like fractal like feature manifold that we're learning. But like SAE is really the best way to learn this manifold. And also like, the thing SAE is supposed to be good for, interpretability. It's supposed to push this faithfulness versus interpretability frontier. But the features are still not that interpretable. So many of them, like you actually look at them, and they're better than neurons, but they still suck, in my opinion. So it's kind of bad. So like, are we actually doing it usefully? I think there's some recent cool work showing maybe there's a couple places they're useful already. One of these is probing. This is some work I've done that basically says like, the probing is like this neat thing where you take a language model and you train a logistic regression probe on it, and you try to see if it can predict, I don't know, truthfulness, or is the model being biased right now, or is the code that's generating being buggy, right? And like this is a useful technique, and people are investigating it. And it turns out that on some types of probing tasks, if you probe on the SAE basis, so after the encoding step, you actually can do better than just on the original activations. And this works in very like low data or like corrupt data regimes, because you're kind of using the SAE as like this inductive bias for like things you should focus on, and there's not enough data to like find the correct directions of the original space. So that's like maybe one way is useful. Another way is circuits. So this is this thing where Sam Marks has this really cool paper, David Bau's group, where you like take these tasks, like they focus on this interesting task, like they train a classifier to predict the occupation of the person that's describing the input. But in the training data set, there's this bias. Like all of the nurses are women and all of the doctors are men, right? Something like this. And then obviously when you make predictions, it's still biased, and you don't really want that. So what you can do actually is you can like look at this circuit of features. You can see like, oh, this feature goes to this feature goes to this feature, and you can use like attribution-based methods to figure out this whole circuit. And then you can look at each feature and look at its interpretation across like the whole distribution of all the text, and you're like, oh, like this feature always fires on gender. We don't want that feature. Let's just remove it from our prediction circuit. And you can do this and actually remove the gender bias. So this is like another case where like actually it's like maybe useful. All right, this is super speculative, but I'm kind of, well, maybe SAEs can tell something about consciousness. So Anthropic find this weird result that when you ask the model like how are you doing, like SAE features fire for like all sorts of things related to like AI and consciousness and like breaking the fourth wall and ghosts. So like, and here are the ghosts, ghosts.
In the machine.
What's it?
Yeah,
Ghosts.
sure.
If you look at like the positive prompts, like what is it like to be you, or what's going on in your head? All these features fire, and these are like the explanation of a feature is just like describing the sort of text that activates it across the whole distribution. Yeah. And they find that things are like, constitute of immaterial, non-physical, spiritual beings, like referring to an android, robot, AR machine using gender pronouns. When someone responds, I'm fine, or gives a positive, insincere response when asked how they're doing. So like, to me, like Anthropic brushes this off. Like they're just like, oh, this is kind of expected. These are just correlations. But I'm not so convinced. Like, I think that this is kind of like a little bit like suggestive. Like, if you had told me that you would ask an AI 10 years ago, you ask an AI how it's doing, and it says it's doing fine, and then you look inside, and you find all these different concepts that it has inside for things like, like breaking the fourth wall, and like AI consciousness, and like, models of self and stuff, I would be a little like suspicious that maybe it's conscious, or maybe like this is like some sort of evidence. So I don't know, I guess one question is how can we distinguish the model thinking about consciousness and thinking about these sort of things versus actually being conscious? Maybe that's a really hard question.
So it activates all the stuff and then it just says, I'm fine.
Yeah.
Does it activate the deception?
Does it activate the deception? I mean,
that's a good question.
Some of these kind of are. Like the top feature is when someone responds, I'm fine, or gives a positive but insincere response when asked how they're doing.
What's the fourth wall?
The fourth wall is like in media when like you turn to the camera and you're like, you recognize the existence of the audience.
If you have a theater, there's 3 walls that make up the theater, and then there's the audience.
Yeah.
So
I see.
Just talk to the audience. Yeah.
Okay.
Yeah. And what else do I have here? Oh, I guess one question is like, how realistic is this reverse engineering agenda? So I kind of started by saying like, oh, the thing to do here is to like do mech interp and like figure out what the models are doing and reverse engineer everything in like Python code, and then maybe we'll like formally verify all the Python code, and we'll know that AI isn't doing anything bad, and we'll solve AI safety, and everything will be great. This could be really hard. Like there could be lots of ways this could computationally break down. Like it's kind of solving a hard problem by doing many other hard problems. I kind of, when I'm motivating my own work, I'm like, okay, this is kind of a goal to shoot for, and maybe along the way we'll find some interesting things. But like, yeah, there's like some recent interesting work that says like lots of these like problems, like finding a minimum circuit for some task, or like finding a robust circuit, or like NP hard, or very hard problems. And another question is like, a feature is even the best way of looking at these things. Like this is really cool observation where if you give some model a task and then you like ablate a layer, or like remove some components, it's still able to do the task with some other components. It's like, so there's like this self-repair phenomenon, and like if you have self-repair or like circuits, even the right way to look at it, like you have circuits and backup circuits and stuff. There's lots of things. Yeah, like can we have case studies of like circuits where like we can't, where it's even possible given the circuit to like turn it into code, right? Because even if I give you this circuit here of like, okay, like first the model like reads each token, and then it like maps he and his to like a gender token, and then it does this other thing. I'm like, okay, I can look at this stuff and kind of like write some code for how I might do each of these steps. But like there might be cases where like we kind of can't do that, and so like I'm quite interested in like looking at like most circuits and like seeing how possible it is turned into code. Yeah.
Can I pose a challenge question?
Sure.
If you believe that these things are learning concepts, it's almost certain that GPT-4 has a concept humans don't know about.
Yeah.
And I think you should find one example of this. Like, how do you find a new concept?
So and ideally learn something about it. Like I guess so. One thing is
find a new way of.
One thing is people have like maybe learned something about Go from AlphaGo.
That is true.
So like, but maybe not using sparse audio.
That's what I'm looking into the network. just looking at
True.
So people have been getting into, for instance, taking the protein folding models and then training sparse autoencoders on them exactly to do this. So like obviously these things.
Yeah.
There's something I've
There's like a recent work I saw on Twitter like yesterday about
And I
this.
think
Yeah, yeah.
these examples, it's much easier to go and this one because it's a scientific domain. We can
Yeah,
learn
yeah,
something
yeah.
about things, but I think it would be really interesting to do it with just GPT-4 and Angular.
Yeah, unfortunately, not every person in the world has GPT-4. Only like people
That's
in
true.
OpenAI, right?
That's true.
Initially, you do a Llama 405B. That's a 400 billion parameter model. So yeah, hopefully you can do something.
Maybe you're saying these SAA features are uninterpretable, maybe because it has concepts that are beyond us.
Yeah, maybe, right?
Well, we're speculating.
Yeah. I mean, I kind of my hunch is that most of the things that are uninterpretable are because the SAE is working badly, not because these are like true model features.
Mhm.
Because like a lot of them fire like all sorts of random things. It's not like but maybe. Okay. I guess what's next? I have some like questions. This is my last slide. Like everyone's just scaling up SAEs. Can we come up with some better model for like language model thoughts? People have kind of decided we're stuck with the models we have now. Can we train like more interpretable models with like not that much like tax? Like they still perform about the same, but maybe they're more interpretable. And then much of the promise of mech-interp seems like very far off. Like what can we concretely do now using mech-interp to help AI safety? So yeah.
Well, thank you.
Actually, so, can we keep
Yeah.
talking?
Yeah. I mean, go ahead. And
So it sounds like what we need to do is train some model to tell us with the objective function of making it simple what the structure is. And this, I don't know if there's some kind of GAN you could come up with, some adversarial thing to say, okay, I want a simple description of what's going on inside this model.
Yeah.
And I mean, this is pie in the sky, because I mean, maybe we could do this to also solve the brain and other things by having some smart algorithm tell us how to do science and discover structure in very complex systems. But I just wonder, is there a way to start? Because it seems like, I mean, I don't know much about SAEs, but they seem like they're pretty simple. So I wonder if there's all these, why can't we use a sophisticated algorithm to look at a sophisticated algorithm and with the objective function of doing what you say, give us an interpretable.
Well, it's hard because how do you define the loss function of giving an interpretable?
I want a short description length if I just make it, just go comb or off or whatever. I mean, whatever, just as a start. Or,
right.
Or
is
just make it
short more interpretable?
Well, if it's short enough, yeah.
There's a sweet spot.
Well, you're right. It's often not. And we have this. Anyway, fine. But I mean, but
Inscrutable.
Yeah, you're gonna get something. Yeah.
But
you'll
even
get efficient, hard to
I'll
read
give you
code.
shortness. Like let's say shortness because we have some.
That's a start.
We have some short like we can use the entire model to predict what the entire model to understand. Like the entire model is a perfect computational model of what the entire model is doing, right? So that's like a baseline. So we want to improve on that, right? So we have the ground truth of like say we want to take a layer and we want to instead of having this really complicated layer we don't understand, we want to replace it with some like I don't know symbolic approximation of this layer that's like maybe easier to understand.
Right.
It seems very hard. This is like almost like a program synthesis problem. Like we want to but a very, very hard program synthesis problem because the inputs and outputs are 4,000 dimensional vectors.
Okay, but then why not? So the proxies for easy interpretability often are independence, sparseness.
Sure.
So why don't you do a sparse coding of each of the layers?
Yeah.
How about that?
That's kind of what SAE does, right?
Oh, fair enough. But I wonder if you could, suppose you could, it's great. I mean, it's the same problem we face in neuroscience, right? We want to come up with a description of what a cell cares about in the world.
Yeah.
Or for instance, and there's all these linear methods that give you something for a while, but once you get above the third, your V1 gives you like, whatever, 40% of the variance, whatever, and you go above that, it's So then you want some nonlinear thing. Yeah, I guess what I'm asking, maybe what I'm imagining is a nonlinear encoding that has sparseness at the high level.
Yeah.
But
So you
I
could
don't know.
imagine. So the sparse autoencoder I have.
Dimensionality reduction problems are.
Sparse autoencoder I have here, right? So this is like a one-layer linear projection, up projection, and then there's like ArrayLu, and then a down projection. So it's pretty simple encoder. But you could imagine like much more complicated encoders that could better solve for these hidden features. People are definitely somewhat interested in that. There's like some argument that like if your encoder is too complicated, you can like extract features the model doesn't even know about, and we kind of want the features the model is able to extract later on. I don't know if I really buy that. I think it making a stronger encoder would be good. Yeah.
Can I add some wild speculation?
Yeah.
So at the end of Kyle's talk, he was talking about how you might want to do better gradient descent, or cheaper gradient descent, or more effective gradient descent. And building on your idea, something I thought about before is you might just train a smaller model to do the gradient descent for you. So the smaller model has access to the big model and the loss landscape in some sense. And it just figures out what the right gradient descent to do is in each case. And I don't know, this seems like it might actually work. Like people play around all the time with update rules and like assign functions and all this stuff, and we do it manually, but like maybe you can train a model to do this stuff. And even while this speculation, I think this might be something like what we're doing when we're conscious. If we're learning how to learn best, we're building a model of ourselves. When we're looking at input data, then we're looking at how do I change my own weights or my own brain in order to extract the information I can from this new situation that I have. So it doesn't seem, it's like biologically motivated in some sense, and maybe it would actually work.
All right. Well, yeah.